Empecemos. Alright, we're live. March 13th. Let's do it. Let's see what we have today. We're ready, and let's go for it. Binary tree with factors. It's binary tree, my favorite. Give an array of unique integers, okay, with each integer strictly greater than 1, okay? We make a binary tree using these integers, and each number may be used for any number of times, okay? Each non-leaf node's value should be equal to the product of the value of the children. Return the number of binary trees we can make. The answer may be too large to return the answer modular. Oh, this is not an easy question. This is not an easy question. So basically what we see here, the non-leaf node has to be the product of the children, and it has to be one of the values in the array. Now, it's very clear from the examples that all the leaf nodes will count, right? All the leaf nodes will count because the requirement was only non-leaf nodes. So that's a trivial case. And then what? And then if we have, say, only one root and one leaf, does that even work? If we have one root and one leaf, I don't think that works, right? It has to be like all of these trees have at least, both children. And it says non-leaf node's value should be equal to the product of the values of its children. What if I only have one child? Does that still count? I guess it's not. Say I have 1. Right? That's a good test case. We're just going to return 0. We want to probe this question a little bit more because I feel like there are a lot involved. Say for 1, what are we going to have? I mean, it cannot have it just 1, 1, 1, right? 1 itself is going to be must consist 2. Oh, I didn't see the requirement. It has to be starting from 2, so you cannot have 1. Because if it's 1, it's infinite, right? So it has to be 2. If 2 is not by itself, then it's impossible because 1 is the only number that can multiply by itself, equals itself. So for 2, I'm just trying to think if it's, well, if you have one child, what about the other child? So I think it's required that all the trees, it's like a complete binary tree, right? Each node, if it's not a leaf node, it has to have two children. It must have 2 children, otherwise this one does not satisfy. It says a non-leaf node's value should be equal to the product of the values of the children. So if I only have one child, then there's no such a thing of a product of the value of the children, because what happened to its other child? The other child is empty. Is that what it is? And if that makes sense, then all of this will have like a 2, and only one child is 2, right? So we're clear on 2 things now. First, trivial case is every value can be the leaf node itself, right? So these are the trivial cases. And then we also have realized that all the trees, all the non-leaf nodes will have 2 children, all of them. It's required. Now, the question now becomes, how do we build the tree, right? So we know that, let's look at the simple case here, 2 and 4, 2 and 4. So we have 2, and we know the numbers are from 2 to 10 to the 9th, which means the value should be strictly increasing. The top value, the root, must be the biggest, right? Because we don't have any non-integer elements in this tree. So if you want, basically, if you think about the whole tree, say we have a gigantic tree, and everybody from the bottom, they're gonna just multiply. It turns into their parents. and the parent is going to multiply times up, which in another word, it just means we're going to have, the root number is going to be the product of the remaining. And then every root is going to be the product of the remaining values. That's what it is, right? So if that's the case, the root cannot be the smallest number. It's impossible, right? The root cannot be the smallest number. And we don't have to use all the numbers, right? There's no saying to use all the numbers. It just say the number of trees we can make, right? The only requirement is each number will be used any number of times. So we can use it or we cannot use it. So that's the thing. We can pick any number, basically. So we can just pick from small to big, right? So we cannot pick 2. We can pick 2, actually. We pick 2, and then 2 can create itself, right? And then that's it. 2 is the smallest, and nothing smaller than 2. And then we'll go to 4. So 4, we can go 4 picked by itself, and then we look to the left and see if anybody we can handle with 4. So we say, 4 is actually, we can make 2 out of 4, right? Because 4 divided by 2 will equals 2. So 2 is 4. So that's good. Actually, you can move on here. Now next we go 5. 5, we know 5 can be itself. And then we look to the left. So if we look to the left, we have 2 numbers, right? We just have to look through the numbers. Well, it's 1,000, so it's 1,000 by 1,000. So O(n) squared, that we might pass. We might pass. So with 5 in a loop, I mean, we don't have to go through every numbers, right? So it's just we only need to go through like half of them. So we go 2 is not working, and if 2 is not working, then 4 is not going to work, right? So because 5, if we do square root, it's going to be 2. So we're going to check and do 2, and then that's 2, and that's not working, right? Not working. So 5 cannot be used as a root. Now we go to 10. 10, we know 10 by itself, it's working. And then we go from front. 10 is 3 point something. That's 3. So we look at 2. 2 is working. So we know 10 going to have another 1. So 10 going to have 2, which is 10 divided by 2 equals 5. 5 is in it. And that's it. So we have 1, 2, 3, 4, 5, 6. There's a 7. Because we can swap. We can swap. If the number is not the same, we can swap. If it is the same, we cannot swap. So actually 10, we have 3, right? So basically just every number we come in. Oh, there's also another part. Like if we have a number, let's say change it. Instead of 10, let's do 20, right? Let's do 20. Then it's going to be different, right? Let's just try it. So we say 2, 4, 5, and 20. Oh, this will be interesting. So 2, 4, 5 will be the same. So 2 is 1, 4 is 2. 4 we can have 2 trees. 5 is only 1 tree. Then we have 20 coming in. Right, 20 coming in. And then 20 divided by 2 is going to be 10, but 10 is not inside, so we cannot use that. 20 divided by 4, we can use, right? So 5, so 4, 5, we're going to have 2, but because 4 has 2 by itself, right? 4 has 2 by itself, which means when we do the 20, it's going to be 20, 24, 5, 25, 4, or 24, 2, 2, right? And so we actually have 3. We actually have 3. So this one shall come up to 7 again. Is this the same as this one? No, it shouldn't be. 4, 5, 6. Oh, 10 by itself, 20 by itself, I forgot. So it's actually 4. So it's 8, right? So this one gives 8. we're still in the probing stage. 9. Well, because we can swap. So swap, it's still okay. Okay, that's fair enough. So 20 actually give us 5. 20 give us 5. Why? Because first of all, 20 by itself, right? 20 by itself give us 1. Then we find 20 and 4. So 4, 5. This gives us 2. And then 4 has 2 in its own, right? So that should actually give us 2 times 2 because each one has 2 more. That's 2 times 2. So 20 give us 5. If we keep going, right? If we keep going, so the next one, let's say, I don't know. What else values are you thinking about? Well, we're thinking about, let's do something interesting. Let's do, actually nothing is really interesting. 100. 40. Let's do 40, right? So if we do 40, we look at 2. 2 and 20. We work. So now it is the complicated thing. So 40, we can go 2 and 20. And for 2, we have only 1, right? But for 20, we have 5. We have 5 different versions, which means it's going to be, so for 20, it should be, no, for the 40, it's 1 by itself, plus, now we have 2 and 20, right? 2 and 20. So 2 and 20, they're going to produce 2, right? And then within each self, 2 has 1, 20 has 5. So this one going to give us 11 just by itself. 40 is going to give us 11. So in total, we're going to have 1, 2, 1, 5, 11. So that's what? This one should give us 20 trees. Let's see if our analysis is correct. 20. Yeah, our analysis is correct so far. So I want to create something that's even more interesting. Yes, 80. Let's do 80. Now it becomes, it becomes a game of combinations and yeah, the combination. So 80, right? 80 we found. So first of all, we're gonna do. Let's follow the procedure. So we're gonna do square root of 80, which give us 8.9. So it's 8. So we're gonna search from beginning until a number is bigger than 8. So 2. Boom, we have it. 40. So 240. That is an answer. So we're gonna have 80 is gonna be 1 by itself, and then gonna be 2 multiplies by whatever we have 2. 2 we have only 1, so it's times 1, and then 40. 40 we just found is 11. So 2 times 1 times 11. Then keep going. 4. 4 we have another one. 4 and 20. So we're gonna do 2 times. What does 4? 4 have like 2 trees, and 20 is 5 trees. 2 times 2 times 5, and then 5. 5 is not working. So that's it. So 80, what we have is 1 plus 22 plus 20. 43. So 80 is going to give us 43. So in total, we're looking at 63. This one shall give us 63. Yes, okay, so this idea is correct. I think the last piece is
Fix it right after you finish.
The last piece is when a number can double itself. So we add a 16 in it. We add a 16 in it. We actually make this even more interesting because after we add a 16, 80 can also be represented by 16 times 5. let's fix 16 first. So 16 is going to be 4 times 4. But now, because it's times by itself, it's not going to be 2, right? Because we cannot swap. So it's going to be 16 by itself, just plus 4. But 4 is also, can we just like multiply? Well, it's going to be not 2 times, but just 1, because we cannot swap, times 4 itself is going to be 2, because it can either be, so we're doing 4, 2, 2, or 4. That is actually 3, dear self. So this is actually special case. Special case is a bit hard. So we know 4 can be represented by 2. 4 can be itself, or can be a tree. So like it's 2 things, right? And then, so what we can do is when this happens, we still say, right? We still say that we can swap, right? But after that, we're gonna just call one, like it's gonna repeat by itself. So it's gonna be, say like 2 times, because it's 4 and 4, right? So 4 is 2, and the other 4 is also 2. And I'm gonna say 2 times 2. 2 times 2, right? 2 times 2. So this will have two choice on the left side, 2 choice on the right side, and then in total we have combinations of 4. But there is this is actually a little bit more complicated. So it can be 4, 4, right? And then we can do 4, 4, and then 4, 4, and then we have the 2. We can lay 2 out. So the only thing we can have is 6, 4, 4. That works. 6, 4, 4, and then the left side 4 we expand to 2, 2. The left side expand to 2, 2. Or 4, 4, 2, 2 completely expand. So there's actually 4 different possibilities, right? Which does make sense because they're all different. And the only thing we don't do is we do not do the top level left and right. Because the bottom level, it still works. So it's going to be 2 times 2 plus 1. That's for 16. So 16 is going to have 5, right? 16 is going to have 5. Now let's look at 80. Now 80 we can do with 5 and 6. And 5 is 1, right? So it's going to be 1 times 16. So that's 10. So 53. So in total, we're going to be 63 plus 10 plus 5. 78. I think this shall give us 78. Let's see, 78. Okay, I think we got it. We just need to code it into a program, a solution. The runtime is going to be... The runtime is actually not good. I mean, it's going to be O(n) squared. That's the runtime. We might be able to get a runtime better if we can. I'm not sure. Just like what we did yesterday, right? What we do yesterday is we figure out a way to make the runtime faster by not looping through itself or looping through the the keys. But here we cannot loop through the keys. It has to be something smaller. Anyway, even if it times out, we need to have the timeout solution first, no matter what. So, pass it in. We know we need math because we have to find the square root. and we need to sort. So the array, that should be fast. Array is only 1,000, right? So we sort the array, and then we go from the for I in range len array, right? At itself. So we need a DP. This is like a DP solution. We need a DP. DP equals 0 times len array, right? And then what we're gonna do is here it's gonna be DP I plus equal 1 because every node can be created as a leaf node. And then we're gonna do for J in range. That is the trick. It's gonna be math dot square root of the current value, and then we're gonna take the int of this, and then we're gonna plus 1. Right. So this is the J's range. Actually, that's not the range. This is not the range. This is actually the value that we need to compare. The range is actually I. In range I, because we cannot go past our current value, so it's before our value. And we're gonna say if array J, we can also say here there will be the threshold. Thresh equals this. So if this is larger than thresh, then we're gonna break. Right now we're gonna consider. We're gonna say if, and then we're gonna create a set, just for array set, make into a set. Now after we make it into a set, now we can check if current value, which is array I, right? If array I divided by array, well, it has to be let's say quotient and with div mod array I divided by array J, right? Now, if R is 0 and Q is in array set, if this is correct, then we know DP I plus equal to 2. It depends. It depends on whether they're the same. So it's gonna be if Q is different, if Q is equal to array J, right? If Q is equal to array J, then we're gonna plus equal to, for the parentheses, to what? DP, DP, oh, 10 to the 9th. DP is not going to be this. DP is going to be a dictionary. Yeah, DP is going to be a dictionary. Actually, DP is not going to be a dictionary. DP is going to be a default dict. So DP is going to be a default dict with int, and we're going to do this. And the DP, not DPI, is not DPI because we are looking at the number itself. So it's going to be DP array I, and here is the same. Going to be DP array I plus equal to DP Q is actual value, times itself, dpq, because we have, yes, that's correct. If this else, if it's not, is going to be 2 times dp array j times dpq. Right? This is when divisible and the q, the quotient, is in the set. Now if it's not, then we don't add anything. Then we until j finishes, and then we go to the next one. Right? That sounds about right. And the result will be when the return sum dp 10 to the 9th plus 7, because we need, I think that is just a big, yeah, that's just a big prime number to make sure that the results is all the same. All right, a little bit test case. There's going to be 3. Next one, 2, 4, 5, 10. This one is going to be 7. Next one, let's try ours. So we have some good test cases that we have conjured up earlier. This one will give us 78. And if we, I don't even remember what the other numbers are. Actually, this one is good enough. They contain a lot of different situations. So I think as long as we get that one passed, this shall work. So we're going to change this to num factory trees array. Run it, and we failed on all of them. That is very unfortunate, but we can take a look. All right, so let's just take a closer look at the first one. We know our idea is the correct, but it's just the implementation, right? The implementation is not right. So what we're going to do is we're going to print out dp and then just take a look. Right, so the dp we print out 2 is 1. That is correct. And 4, oh, it's because the sum, dp is no longer an array. dp dot values, right? So that is what we need to change. And now we pass. Okay, try it again. Now we all pass. Now the problem is whether this is fast enough. I'll run the code first and submit. Let's hope that, oh, got it. I was going to say let's hope it's not too slow, but we got it already. Oh wow, this is one of the few times that we had a pretty good runtime. It's 93%. Pretty good. I think we revenged 2 days ago, right? So we had, no, 3 days ago. We have the day before yesterday was a bad day. And then the day before yesterday was a bad day either. So we have 2 bad days. And yesterday we revenged the day before yesterday. And today we revenged the day before yesterday, which is great. Okay, let's write our intuition. So the intuition is using dp from the question. We can have 2 basic findings, right? 2 basic findings. First, each number can at least create 1 tree, which is a tree of only the root. Second, since all the numbers are integers, it is the root must be bigger than its children. Therefore, we can sort the original array and traverse from left to right. For each number, we can examine the values smaller than itself and see if there are any value, any number that is divisible, and the quotient is also in the array. And since we are traversing from small to big, actually we can put this one later. Small to big values, to big numbers. Each time a new number is examined, all of the numbers smaller than it must have been examined already. This is a perfect situation for DP. Now the trick is only when we find a valid pair, right? Find a valid pair for a root number. How many trees in total can we create for this specific root? Well, say we use DP to record the number of trees each root value can create. Then for a root value, like to say root value x equals y times z, then for the number of trees that can be created based on x is dp is 2 times dp x dpy times dpz if y not equal to z, or dpy times dpy if y equals z. And that's it. We go through the entire array, sorted of course, populate the DP dictionary. Cannot use array because the values can be way too big. And eventually return the sum of all trees, all number of trees for each number. So this is going to be O(n) squared because we have to, O(n) squared. And I just wrote Pn squared, O(n) squared. And then 160 milliseconds, and we got a 93% ranking. This is amazing. I'm thinking about here, maybe we can do some trick, right? So what we know is this can be valued as 1, right? Which means if it's 1, we need the value to be 1. If it is 0, we need the value to be 2. How do we do that? Well, we can do that by applying a trick. So, which means I think I know. So we just need to do this times 1 shift left q not equal to array j, right? So if I say one shift left, let's just put more parentheses just so that we have clear. So this will evaluate to true if q is not equal, and if it is 1. So 1 shifted by 1 becomes 2. We good. If this evaluates to false, which means q is equal to this, and this will evaluate to 0, then 1 does not shift, and then this one shall pass as well. Yep. Multiple spaces between operators. All right, so this is just a little bit smarter here. Okay, we can go take a look. Wow, this is good. It's a medium question. No question asked. This is a typical medium problem. And usually, I think dynamic programming most likely is a medium problem. Yeah, it's a medium problem. Dynamic programming, and I just read through it. If root node of the tree has children x, y, then there are ways to make this tree. In total, in the sum, yeah, I think we have hit it pretty well. Let's just take a look here. Sorted, yes, we have to sort. DP, and this is something we don't. Oh, it used I and J instead of this. Oh, but did they say it's all unique? Oh, unique integers. Ah, I and J to do this. Now we get a little bit more complicated here. And then they just need to have, they need to have this. So we have the DP set up as a dictionary, right? And then we loop through and we take the values itself. And then here they use the index, right? You use the index, and then they need to use a dictionary to refer to what numbers we're talking about. So let's say just go this and go this exactly, and then if it's divisible, we get it right, and if it's right in, then we don't need a separate set. That's good. And then this will be this will be this times this. We go through each one of them, so we don't even have to check. We just go through each one of them. It's probably the reason why this one's faster, because we run a check. Now we run a check, so we stop it. We didn't go through the entire thing. We stop it first, and because we stop it, so we have to do this, right? We have to do this. Yes. Good. No, that's not correct, because we are going through everything. Bless you. Wonderful, wonderful. I'm telling you guys, this is how a sneeze should be. There's great power. The earth has just has shaken. I can feel the ground shaking. That's a healthy sneeze. Only the powerful can do this. All right, I actually like this. I like this better than my solution. It's cleaner, right? It's like in mine, it's a little bit cluttered here and there. It's but it will be slower. Never mind. We didn't try it. We didn't try it for sure. This most likely come from a contest as well. All squared, 2019, a long time ago. Anyway, it's the same. It's the same one. Oh, did he not sort? He sorted. Yeah, he did sort. Oh my God. He wrote in. Oh, wow. Let's not do this. Now, these people are special, so I give them slack, Mr. Parkman. All right. What is this? For B and A, if B is smaller than A, okay. And then every time I'm gonna get we're gonna sum plus Oh, good. Very good. Very, very good. All right. Here's what we're gonna do right now. We are going to go to submission, and we're gonna rewrite this in the. You want to write this in the smart way, like the two-liner or three-liners, or I'm thinking. So we need a DP, right? And this one's different. This one's going to be times length this. And what we're going to do is we're going to say for for nope. I'm going to turn this into a dictionary. Turn this into a dictionary. Step and Parkman's solution. I think it's a better solution. I like that logic flow better. So we're just going to say for A in sorted array, right? And then for A in sorted array, what we're going to do is we're going to say DPA something. Now that something going to be when it loop through from the beginning every value that is smaller than A. So we don't worry, right? We don't worry. It's going to be O(n) squared no matter what. So we don't worry. So we're going to say going to be for B in array if B is smaller than A. Exactly. So it's going to be like this. And for each B, what we're going to do is, what are we going to do? Is to do dpb times dp.get A divided by B. Hold a sec. If we want to do this, it's an interesting thing I'm just thinking about, because when we pass it in, we're passing in a, let's just say A1 equals 2, right? So it's A 1.0. Oh, it does evaluate to 1. However, if we say A 1.00001 equals 3, then we call A1 as 2, A.00 still 2, 0, 0, 1. They probably just turn it into a string. I don't know how the hash function works, but I don't know how that works, but I think if I do this, it works. And then we can get 0, right? So like that means if it does work, then I get it out, times it. If it does not work, then it's going to be a floating number that doesn't fit, and then it'll give me 0. So it's just by itself. And that's it. That is it. We're going to return sum dp.value